Okay, so today I'm glad to have Cezar from Tsinghua. He will talk about Zagier's formula for multiple zeta values, and it's order variant revisited.
All right, thank you very much, Konglin, Daland, and Cosmin for this opportunity to give a talk here. Well, I could tell you this is a premiere for me to give a talk at 4:30 a.m. in the morning, but well, it looks like I have to do this once in my lifetime. So today I will talk about Zagier's formula for multiple zeta values and also its odd variant, in fact, which is what we call the multiple t values. And this formula has very sparked a lot of interest lately, especially now due to its wide range applications, even in physics now, in quantum field theory and so on. So first, let me start with multiple zeta values. Let me give you some context first. So multiple zeta values are these numbers that you see here, zeta of K1, Kr, which are defined as this nested sums, right? So sum over all ni's, n1 less than n2 less than nr, or 1 over n1 to k1 times nr to kr. And for this to make it make it look convergent, so we will require that all these ki's from 1 to all the way up to r minus 1 are positive integers, and kr to be greater or equal than 2. Anyway, these numbers, they converge very slowly. And although they look very simple, they have deep connections with, well, whatever you can look at in knot invariants, quantum groups, Galois representations of the fundamental group of P1 minus 0, 1 and infinity, mixed state motives, or even Feynman amplitudes in quantum field theory. So we will call this from now on multiple zeta values of weight. Well, I put absolute value of k, of weight k and depth r. Well, where k will be the weight, so this will be the sum of all these ki's, and the depth will be r. So obviously there are 2 to the power k minus 2 all together, but for r less than the weight, there are k minus 2 choose r minus 1 multiple zeta values of a given weight k and depth r. So we're interested what kind of linear relations we can see between these numbers. But before we go into that, let me go back to something that we know, something that's more classical. So let's see what happens in depth 1. So in depth 1, we will have the so-called single zeta values or Riemann zeta values. And this goes back all the way to Euler, right? Since 1734, Euler proved that, in fact, he didn't discover, it was a conjecture. He proved that zeta of 2 is pi squared over 6. And moreover, a bit later, Euler actually generalized and found an exact formula for all even values of the zeta. So this, as you can see, it's related in terms of the Bernoulli numbers. This is like pi to the 2k times a rational number. Also, in terms of Bernoulli numbers, you can express the values of the Riemann zeta function at negative integers. Again, it's in terms of the Bernoulli numbers. And we can actually evaluate this. We can evaluate the Riemann zeta function at negative even values. And these are nothing else than just the trivial zeros, which were also deduced by Riemann from his functional equation. All right, so also we can evaluate, zeta of 1 minus 2k. We can see what happens at 0, at -1, and so on. Zeta of 1, we have a pole here, so zeta of 1 does not exist. But we will see that we can actually do something about it later on. We can actually regularize this in the context of of multiple zeta values. But there is a mystery about the odd zeta values. So we were wondering what's happening with the zeta of 3, zeta of 5, and zeta of and so on, zeta of 2n plus 1. So in other words, we would like to understand the polynomial relations in terms of these odd zeta values and pi. And just like I said at the beginning, this will turn out to be equivalent with understanding Q-linear relations in among multiple zeta values. But anyway, we'll get to that point. So let me go back a bit about these mysterious odd zeta values. So at this point, very little is known. Well, if I want to go back to Lindemann, where he proved that pi is transcendental, then the groundbreaking result of Apéry, who proved that zeta of 3 is irrational. Well, since then, there is another result of Ball and Rival, and they proved that the Q vector space spanned by odd zeta values is infinite dimensional. So in particular, there are infinitely many irrational numbers among the odd zeta values. And of course, there are some other results here, but I don't want to get into that. And also another result, a significant result, was by Zudilin in 2001, who proved that at least one of these numbers, zeta of 5, zeta of 7, zeta of 9, and zeta of 11, is irrational. So just like I said earlier, the ultimate goal will be to prove this old Folklore conjecture that the odd zeta values and pi are algebraically independent over Q. So in other words, we would like to understand polynomial relations among these values. Okay, so now this is the story in depth 1. So as you can see, we don't know too much about it. So we'll try to kind of go around this old Folklore conjecture, this algebraic independence conjecture. But before we go into that, let's see what happens in depth 2. So in depth 2, we deal with double zeta values, and for double zeta values, so the double zeta values are these numbers, zeta of k1, k2, or these double sums here, right? And the way to obtain these double zeta values is just to multiply 2 single zeta values. And as you can see here, once we multiply 2 single zeta values, we can split this just and do it in a naive way, just like Euler did it. So we can multiply zeta of k1 times zeta of k2, and we can split this sum. So as you can see, we have this sum here. And we can split this into three sums, right? The first one was when n1 is less than n2. The second one when n2 is greater than n1. And the third one when all 3 of them are equal, right? So we have this is equal, and this is this. So in these 2 cases here, we'll have 2 single zeta values, right? Double zeta values, sorry. So we have these, but in this case, when n1 equals n2, we will have 1 single zeta value. So basically, this is just a baby example of what we call the Stoffel product. Well, as you can see, this is a way to generate double zeta values when you multiply 2 single zeta values. In fact, when you multiply their series representations, we will see it later on that you can actually do something else too. For example,
can you explain the word Stoffel? What that word means?
Stoffel product. So it's like a kind of a shuffle when you shuffle the deck.
Okay, yeah.
But it's not quite the shuffle, because you see you have to take into account the order here. So n1 less than. In fact, yeah, when you like a shuffle, let's say.
Okay, I see. Okay. Yeah.
So in this, for example, in particular, if you want to play around with zeta of 2, since we want to go back to Euler, we can replace K1 equals K2 with 2, and then we'll get that the double zeta values, double zeta of 2 is pi, is a rational multiple of pi to the 4. All right. So this is just an operation, one of the operations that we can do. So the Stoffel product, in fact, we can define this in a much more general way. So here I just did it for 2 single zeta values, but in fact, you can multiply, for example, a double zeta value. For example, you can multiply zeta of K1 times double zeta of K2, K3, and you do the same thing. So in this way, you generate triple zeta values and so on. All right. But now, like I said, there is another, we can do something else to these multiple zeta values. And in fact, this was an observation made by Kontsevich, in fact, who actually showed that, that these multiple zeta values are what we call periods. So in the sense, so these are, well, the periods, the naive periods in the sense of the definition of Kontsevich and Zagier given by in this paper. So this is what we call naive periods. So, well, since we have this kind of representation, we can actually multiply, we can multiply 2 single zeta values. And in fact, we'll not multiply their series representation, we'll multiply their integral representation. So we can do the same thing. For example, let me just give you some examples. Here I just want to mention, so basically you can we can represent multiple zeta values in terms of this. Here, I want to specify that this is an iterated integral. Is not the integral from 0 to 1 because it doesn't converge there. So it's the iterated integral. So just over these one forms, right? dz over z, and so omega 0 is given by dz over z, and omega 1 is given by dz over 1 minus z. So let me just give you some examples of, and some examples, let me see, for single zeta values, you can write zeta of 2 as the integral over t1 less than t2 less than 1 of these dt1 minus 1 minus t1 dt2 over t2. So as you can see here, I have omega 1 here, omega 0, right? So this goes back to even Leibniz. In fact, you can, it's an very nice exercise to prove using geometric series expansions, or expansion of 1 over 1 minus t. You can actually prove it. Also, here you can write the zeta of 3 as an iterated integral, or you can actually write a double zeta, zeta of 1, 2. As you can see, these two look different. They're in the integral representations of zeta of 3 and zeta of 1, 2. They look different, but in fact, we will see that these two numbers are actually equal. This will be another result of Euler. Or if you want to go even a bit further in weight 5, right? We have double zeta values, double zeta value 2, 3, you can represent it as an iterated integral this way. So now we can play around with this iterated integral. We can multiply them, and then we can obtain some other collinear relations among these multiple zeta values. So in other words, let's do it. Let's do an example. So if we do this example, just like we did for the series representations, we can do it for their integral representation. So imagine, so you multiply this, and now it's just like the shuffle. So you imagine like you shuffle a deck of cards. So you have the first one is the integral over t1 less than t2, and the second one s1 and s2. So you shuffle all of them. And after you do all these computations and you take into account this, the one forms here, actually it's very easy to see, you will end up with this relation here. And as you can see, the main difference between the stuffle and the shuffle product is that here you have only double zeta values. So there is no way you can obtain single zeta values. In the case of the shuffle, if I go back, you see you have a single zeta value here. When you multiply two single zeta values. But in the case of the shuffle, it's only double zeta values. And in this way, we know that zeta of 2, 2 from the Stoffel, it was pi to the 4th over 120. And now we can actually get the relation for zeta of 1, 3. So this is just an example, and you can play around with other examples. You can multiply zeta of 2 times zeta of 3.
Sorry, Cezar, is this how this identity is proven in general? This Drinfeld-Kontsevich, you do some kind of, you have these operations, Stoffel product, shuffle product, and you do some kind of induction on.
You mean this identity here?
Yeah, yeah, the original theorem. Does it have an elementary proof?
So yes, it does. But the proofs that I know are in terms of polylogarithm functions, like special functions. Just.
Okay, so you cannot really get it just by some naive induction on R, on the sum of K1 plus K2 plus KR and some identities like this.
Not that I'm aware of. I mean, I don't think you can avoid the polylogarithm.
Okay, very interesting.
Okay, so
also in these integrals, doesn't the gamma function show up somehow?
Euler's gamma function?
Yeah.
Not exactly in these integrals, but something related, yes. At some point it will appear.
Okay.
So this is, you see, for example, another example, let me give you, of shuffle product, right? So you see, this time we multiply zeta of 2 and zeta of 3. In the first case, you see, we have like, this is in weight 2. We multiply two single zeta values, but the first one is in weight 2, the second one is in weight 3. And of course, we're gonna obtain only double zeta values, as you can see here, zeta of 3, 2 plus 3, zeta of 2, 3 plus 6, zeta of 1, 4. So you can see there is 10 of them. And again, you can play around like this with all the values. And in fact, general version of the shuffle product, which is not trivial to see, but you can prove it in an elementary way. So when you, okay, here is a mistake. So this is K2. So zeta of K1 times zeta of K2 is, you can write it in this way. So is this sum when you have these binomials. And here, as you can see, this is a double zeta value. So there is no way you can obtain a single zeta value. So when you do the shuffle product. So now you have.
When you do the shuffle product, what's the next step? You're gonna change like the S1s to be dependent on T or something? After you, how do you decompose it into a sum after you write it as a?
Yeah, you can prove this. In fact, yes, when you multiply two single zeta values, their integral representation, you will obtain this. But in fact, you can prove this by some kind of a decomposition, fraction decomposition, and use some very tricky induction argument. Okay. The proof is elementary, like I said, but is not trivial at all. So, but this is the general formula for the shuffle product. So you have a general formula for the Stoffel, which was simple, as we have seen, and this is, which is not that simple. But this is not just the end of it. We can actually, at the beginning, we said that zeta of 1 is does not exist. But in fact, we can allow you can regularize these multiple zeta values. In other words, we can allow KR to be 1. Well, when we defined them at first, we said that KR has to be greater or equal than strictly greater than 1, so that it will converge. But we can regularize them.
Sorry, just before you move on, I wanted to ask this shuffle product identity. The only proof is using the integral representation.
This one here.
Yeah, or no? It's just.
No, it doesn't use the integral representation.
Okay, sorry.
Yes, you just expand fraction. Yeah.
Okay.
So let's see, let's multiply now by zeta of, so let's regularize the multiple zeta values. So to regularize, we have to multiply by the divergence here. So zeta of 1 times zeta of 2. So if we do the Stoffel, you have zeta of 1, 2 plus zeta of 2, 1. So again, we have two double zeta values, but we also have a single zeta, which is zeta of 3. But when we do the shuffle regularization, we will only going to have like two double zeta values. So we will get like, when we multiply the integral representation, we will get that zeta of 1 times zeta of 2 is 2 double zeta of 1, 2 plus double zeta of 2, 1. So here, this will give us the first known trivial relation for the double zeta values, which basically we call a double shuffle regularization. So this was given by Euler in 1775. Of course, Euler didn't prove it in this way. So that zeta of 1, 2 is zeta of 3. So now, so basically, there is actually, before I move on, let me tell you one thing. There's actually a conjecture here that these, well, still a conjecture, that these double shuffle regularized relations will give all the relations among the multiple zeta values. It's still a conjecture, but that's the conjecture. So it's conjecture that these are the all the relations that we need for multiple zeta values.
And, and what do you get for zeta, for the value of zeta 1 if you like solve this equation? Like
for here, for example, so if you equate these here, right?
Yeah.
Because you will get exactly Euler.
Yeah, I know that I understand, but I ask if you can like give a value to zeta 1 that.
Yeah, what value you will give 0 usually.
Ah, you'll give 0 to zeta 1. Okay.
Yes.
Okay.
So now we would like to understand a bit more about this vector space, basically, of multiple zeta values. So if we denote Zk, the Q vector space spanned by all multiple zeta values of weight k, so this conjecture of Zagier will imply the algebraic independence of all zeta values. In fact, the transcendence conjecture that I just mentioned at the beginning. So in other words, the dimension over Q of this vector space is this Fibonacci type number, which comes from the power series expansion of 1 over 1 minus t squared times t cubed. And I'll show you an example how to understand.
Sorry. This is a little bit confusing. So you really mean algebraic independence? So you mean like this is a Q bar expansion, a Q bar span or Q span?
Q span.
A Q span, then this is linear independence, right? I mean, not
Yes.
algebraic independence. So then right? So it's not
the algebraic independence of the transcendence conjecture. So this conjecture of Zagier, this dimension conjecture will imply the algebraic independence of all zeta values in pi over Q.
Implies okay. So this is stronger than the algebraic independence, right?
Yes, exactly.
So this conjecture is so now probably I can ask this question. So is it whether or not it's true that the Q bar span and the Q span has the same dimensions?
Yes.
Is no?
Say that again.
Is it known or not? Is it proved or not?
That what that?
Yeah, I mean, they are. I mean, it's like the algebraic independence is equivalent to the linear independence, right? I mean, if you just take the Q bar span of all the multiple zeta values of with k, whether or not it has the same dimension as this dimension zk. Right?
Yes.
So does it have the same dimension?
Yes.
Now, how do we know that? This seems pretty.
So you say that? You mean when you add all multiple zeta values?
Yeah, I mean, if you take
I'm not sure I understand your question.
So now you are taking the Q span, the Q span inside C, right? Inside complex numbers of all the multiple zeta values. and consider the Q bar space over Q, right? And I can also consider the Q bar span of all these values. Consider the span as the Q bar space, and consider its dimension. Whether or not they have the same dimension. So the latter one is definitely smaller than the former one, right?
Yes.
Are they the same? I mean.
This sounds incredibly difficult, right?
Yeah, exactly.
I don't know.
For instance, I don't think it's known that zeta 3 is in. So you know it's irrational, but you don't know it's in Q. I don't think you know stronger statements about.
Yeah, exactly. In fact, that was my.
Yeah, for example, already for zeta 3, it's already hard, right?
Yeah. In fact, I will show you the next slide. Actually, I think we'll give a answer to this. So, in other words, we would like to see what kind of Q-linear relations do we have. So what kind of Q-linear relations do these multiple zeta values satisfy? So let's see in small weight what's happening. So in weight 2, as you can see, we have only one. So it's a single zeta value. So it's zeta of 2, which is, we know it's a rational multiple of pi squared. Then in weight 3, as we have previously seen, we have 2 of them. So we have zeta of 3 and zeta of 1, 2. Again, these 2 are equal. In weight 4, we have 4 relations. So we have a single zeta of 4. We have 2 double zeta, zeta of 1, 3, and zeta of 2, 2, and 1 triple zeta of 1, 1, 2. But in fact, anyway, all 4 of them can be proven that are rational multiples of pi to the 4, right? And in weight 5, the problem gets very, very complicated. In weight 5, there are 6 linearly independent relations among these 8 numbers. So as you can see, we have zeta of 2, zeta of 5, zeta of so we have 8 of them, as you can see them here. But there are actually 2 of them that gives us some problems. And these 2 are zeta of the one highlighted in red, zeta of double zeta of 2, 3, and double zeta of 3, 2. In fact, we can express all the others in terms of these 2. So we would like to understand what's going on with these values, with zeta of 2, 3, and zeta of 3, 2. So let's see if we want the Zagier conjecture to be true. So let's see what happens in weight 5. So as you can see, in weight 5, we can express, just like I said, zeta of 5, zeta of 4. This is in fact the duality theorem. Anyway, I'm not going to go into details about that. But if I want, as you can see now, from these examples, one can infer that the dimension is less or equal than 2, right? We have these 2 here. But if I wanted the Zagier conjecture to be true, so this will be equivalent with zeta of 2 times zeta of 3 over zeta of 5 is irrational. So just we don't even know for D5 how to prove that zeta how to prove that D5 equals 2. But of course we have that is less or equal than 2. So in this direction, there was this conjecture made by Hoffman, which now was proven by Brown, in fact, which says that every multiple zeta values of weight k can be expressed as a Q-linear combination of multiple zeta values of the same weight involving 2s and 3s. So as you can see, as you have seen, for example, if I go back here, look at this example in weight 5. You see all these multiple zeta values can be expressed in terms of zeta of 2 and zeta of 2, 3, and zeta of 3, 2. And the same goes in any fixed weight. So this was a conjecture made by Hoffman back in the days in 1997. Well, many people attempted this. But it was proven by Francis Brown in 2012. And in fact, well, he used the so-called motivic multiple zeta values. So his proof uses motivic arguments. And in fact, he reduces the problem in evaluating this family, or this Hoffman family of multiple zeta values involving 2s and 3s, and these copies of 2 and a single 3. So using the motivic arguments, the best he can do was just to write this as Q-linear combinations of products of pi to the 2m times zeta of 2m plus 1. So as you can see, powers of pi and odd zeta values. Well, so if he needed a proof for this, and there is the Zagier found a formula and its proof. So the formula looks, well, it looks ugly at first, but actually it's a very beautiful formula. And I've been obsessed with it for a while. So the formula for evaluating this Hoffman family of multiple zeta values is given by, as you can see, this is the simplest Hoffman family, Hn, which, well, let me just say that when I write here zeta of 2, and this means that zeta of 2, 2, and copies of 2. So Zagier proved that HAB, so this Hoffman family involving 2s and 3s, can be expressed in terms of this finite sum. And as you can see here, I have this HA A plus B plus 1 minus K, but this will depend on the weight. And also, as you can see, I have the odd zeta values here. And of course, what Brown couldn't achieve using motivic arguments is to find these the exact formula of the coefficients, which were found by Zagier in this paper. Anyway, so maybe I'll just say a few words about Zagier's proof. Well, Zagier's proof for the formula of HAB is indirect and very complicated. So in other words, basically what he does is the following. So he constructs two generating functions. And the first generating function has the first HAB coefficient. And then the second generating function has this H hat AB, which H hat is nothing else than this guy right here. So this is H hat. So in other words, he tries to show, he shows that these two are equal indirectly. So in other words, he showed that these two functions, are entire functions of exponential growth, which agree at sufficiently many points. So in this way, the equality can be forced of the two functions, and then therefore these two coefficients will be equal. So that's the proof of Zagier. And now let me make a parallel with something else. So we define multiple zeta values, but in fact, we can define also the odd variant of multiple zeta values, which will be. Yes.
What does, so can you go back to the previous slide? I'm going to ask a stupid question probably. So H hat is the right hand side in
yes,
Zagier's.
this one here.
But Zagier didn't know, right? What's the right hand side? So Brown didn't conjecture this formula, right? He just
no. Zagier actually that's a very good question, because Brown didn't conjecture this formula. In fact, Brown said they didn't even know the formula. So Zagier guessed the formula based on some experience. In fact, in his paper in Annals, he actually says in one page like how he guessed the formulas, how he looked for patterns, he put it on a computer and so on, and then he guessed the formula, and then he will prove it.
Okay, that's very interesting. So from this expression on the right hand side, I guess there are some factors of pi hidden there. No, it's
yes, yes, exactly. Yes, they're right here in this here, because we have this expression here.
But this is not always even, right? If you sum from k equals 1 to a plus b plus 1, this argument.
Yeah, but it's an argument. It's not, you cannot take it out. I mean, it's not like, it depends on the.
So it seems like a very wild guess to me.
Well, he
based
made
on
it.
Brown's conjecture, but
Yeah, in fact, they needed this formula. So, in fact, many people try to find this formula. Pierre Cartier, even Delin, but Zagier was the one that actually succeeded, and he proved it. No. So, like I said, his proof is very complicated. So, in the same way, we can define the multiple t values, or which come from this. Well, in the same way, we can define first multiple Hurwitz zeta values, because you can see them, zeta of k1, kr, a1, ar. But we're more interested in this special multiple Hurwitz zeta values, which we call multiple t values. So these are what we call the multiple t values. And in fact, they're pretty recent, as we will see. So as you can see, these are what we call the odd variant of multiple zeta values of MZVs, right? So again, we try to see what kind of maybe what kind of parallel, what are between these multiple t values and multiple zeta values. And in fact, they were initiated by Michael Hoffman again. So I forgot to say at the beginning. So the theory of multiple zeta values just begun in the early 90s with independently by Michael Hofmann and Zagier. So Michael Hoffman defined them in this paper pretty recently. So we would like to see what kind of parallels are there between these multiple t values and multiple zeta values. It looks like they share with the Stoffel multiplication, which is pretty, well, easy to see. So again, we can multiply two single t values and you'll get the same thing. You can multiply two single, or you can multiply a single t value with a double t value, and then you'll get these relations here. Okay, but unfortunately, if you're trying to go for a iterated integral in the same way as you want to express the multiple t values in terms of a very nice iterated integral, that's not going to happen. Unfortunately, the iterated integral expression, the integral representation for multiple t values will differ drastically from the one of multiple zeta values. And let me just give you an example so that you can actually see it. Just look at this example. So if I'm trying to find the analog of Euler's relation, right? Just like for t1, 2 is, I have this extra term like here, like log 2. And unfortunately, this will happen. So once you start building linear relations, if you're trying to build linear relations, just like in the same way as you tried for multiple zeta values, you can just forget about it. That's not going to happen. You will have these extra terms here, like log 2, and even worse, you'll have even alternating multiple zeta values and so on. So as you can see, this is just like we can generate an algebra, but this is quite different from the algebra of MZVs. So, well,
probably I have a question. So if I remember correctly, for multiple zeta values, the relations are always between the values of the same weight, right?
Yes.
But here you have a different weight, T2 here. 2 and 3.
Yes, exactly. Exactly. That's a very good observation. So as you can see, not even the weight is the same. So
yeah.
So we run into problems. So so as you can see, this example just show you how different they are in some ways. But maybe we'll try to look for other similarities.
Sorry. Probably I have a stupid suggestion. So is log 2 some kind of a regularized T1 up to a Q multiple?
That's actually a very good question. T1.
Suitably regularized.
Nah, it's not. Log 2 converges to log. No, I don't think so. But actually, so you're trying to suggest that maybe not. So it should be some kind of anyway. So in this way, we're wondering if we can prove some kind of a Brown type result involving these empty and multiple t values. And in fact, very recently, in fact, this year, in some cases, multiple t values are linear combination of multiple zeta values. And this was proved by Murakami, that t values are Q-linear combination of multiple zeta values. And Murakami actually proved a Brown type result. He actually showed that every multiple zeta value is a Q-linear combination of elements, well, the same way, involving 2s and 3s. So this is an analog of Brown's theorem, and it was published very recently in this paper. And in fact, he basically mimics Brown's and Zagier's paper verbatim, basically. And he tries to find he reduces everything to evaluate this family of multiple t values involving 2s and 3s. So in other words, Murakami proves this theorem. So as you can see, he defines this multiple t values in a different way that I define them. So I put 2 to the negative. Here I put the negative in my case. So, so it's like a similar Zagier formula, right? But anyway, forget about this formula. I just wanted to write it just the way he did it, because we'll prove something equivalent. And Murakami proves, like I said, just basically mimics the same thing as Zagier. So he defines these 2 generating functions, and in fact, his computations are even much more complicated than Zagier's. I don't know why, where the extra terms come from. I didn't watch closely his proof because it's very tedious and it's like 15 pages long computations. But we can have an equivalent version of Murakami's evaluation. As you can see here, I will define it in my own way. So I define it the TAB, this family of multiple t values with 2s and 3 and a single 3. But you see, he doesn't have this term, so I'll have this term. Anyway, it's not a big deal. But as you can see here, I can express this again as a Q-linear combination of powers of pi and odd zeta values. So this is the equivalent version of Murakami's theorem. And again, basically everything reduces to evaluate this family of multiple t values to prove the analog of Brown's theorem. So the purpose of this talk is to unify the 2 theorems of Murakami and Zagier and prove them directly and much simpler than they did in a unified way. So in a much more elementary way. So what we're going to do is the following. So we're going to have we're going to start with a little bit of ingredients. So the Gauss hypergeometric function, as you can see, is defined as in this way: is 2f1 of ABCX. So it's defined as the series here. And the funny thing is that I can obtain from the value of the hypergeometric function, I can write cosine of arcsine and sine of arcsine, and doing this trick, I can obtain the Taylor series for the integer powers of arcsine and of the arcsine. So we can obtain the even powers, and as you can see here, we have the multiple harmonic sums. So multiple harmonic sums. And here I will have the odd version of the odd variant of multiple harmonic sums. So this will be my starting point, and the proof will be elementary. And this will be combined with values of Clausen function. So Clausen function, Clausen integral, is this, or Lobachevsky function, usually it's called. The funny thing is that I didn't even know about this function existed. So like very few years ago, like 4 years ago. So it's defined in this way. It's defined as this integral from 0 to theta of log of 2 sine of t over 2. And you can write it as it's in Fourier expansion of the sine of k theta over k squared. And of course, you can define the higher order Clausen functions, right? The even higher order Clausen function and the odd higher order Clausen functions in this way. As you can see, these are the Fourier series expansion. And what's important here is that you can relate the values of these higher order Clausen functions in terms of odd zeta values. And in fact, we will need this to prove this important lemma, which will be essential in deducing these two formulas. So it's surprising that we haven't seen this. When Derek published this paper, he was shocked to see that there is no formula for this integral. It was very shocking, although it's very simple. So you can express this as the integral of x to the p times cotangent. As you can see, this is a finite sum involving odd zeta values. And the proof actually it's very elementary, just integration by parts and using properties of Clausen functions. So instead of writing x to the p, we can actually write a polynomial, and we can have this version of this of the lemma. So if we consider a polynomial, so we can express this integral of a polynomial times cotangent in terms of this finite sum of involving odd zeta values and values of the derivative of the polynomial. All right, so that's all that we need at this point. So now we can prove, we are ready to prove Zagier's formula and Murakami's formula. So first, we will relate this HAB, so this this Hoffman family of multiple zeta values involving twos and a single three. We will relate this in terms of this cotangent integral. Well, at first it looks surprising, but this is not surprising since we previously seen this dilemma that that involves the polynomials in the cotangent function. So this theorem will have two ingredients. So the first one is just to use the Taylor series for even powers of arcsine, which we have seen previously, which will give us this formula here. But now we have to deal with this tail, or with this arc cosine of x. So the moments of arc cosine of x to the power 2b plus 1 are related to the tail multiple harmonic numbers, which will be given by this. So these two ingredients will just give us this first part, right here. But now we have to relate this integral to the Q-linear combination of all zeta values. And in fact, we can do that. Surprisingly, this integral can be expressed as this coefficient here, factorial some powers of pi, and h hat of AB. And this is just applying the cotangent lemma for this polynomial. So this cotangent lemma here, you just apply, we take p of x to be equal to x to the power 2a plus 2 times 1 minus x to the power 2b plus 1. And Zagier formula will just follow immediately as a consequence. So it's a very direct, very elementary proof. Well, guess what? Since we talked about how parallels and differences between these, between multiple zeta values and multiple t values, we can actually do the same thing. And it's striking how similar these two formulas for for HAB and TABR. So as you can see, they're almost the same. The only difference is that in the case of HAB, this integral here has it was 2a plus 2, and here is 2a plus 1. So that was the only difference. So in this case, I will use the odd powers of arcsine of x. And again, by just mimicking the same argument, I can relate this cotangent integral in terms of t hat of AB. So again, I apply the same cotangent, the same lemma, but this time I will apply it for a slightly different function. So in this case here, you've seen that we applied for x to the power 2a plus 2 in case of the multiple of zeta values. In case of the multiple t values, instead of 2a plus 2, it will be just 2a plus 1. And it's the same thing. And again, the equivalent version of Murakami's formula will follow immediately. Well, there is actually, well, I don't have time, but there is also some, maybe you're wondering how, if this Zagier formula will give us some kind of arithmetic information about odd zeta values, about the ratio of odd zeta values and powers of, and odd powers of pi. But anyway, that will be will be devoted for another work in progress. So I guess I'll stop here. Thank you very much. So I just want to mention this is based on this paper jointly with Li Lai and Derek Orr, which is on arXiv. So thank you very much.
Okay, yeah, that's thanks Cezar for the great talk. Okay, so to the audience, have questions?
Does this method allow you to get other identities for things that are not only 2, 2, 2, 2, 3, 2, 2, 2, 2?
That's actually a great question. So for example, you're wondering, what if I go, so for example, what if you want something like zeta of 2 to 2 instead of 3, let's put 4, right? Something like that.
Yeah.
Actually, we're working on this.
Okay.
In fact, I even talked to Zagier, and he's interested in evaluating this. Instead of putting a 3 there, put an M.
Oh, okay.
So he wants this, even in the special case when these are 0, so B is 0. Even in the special case, he needs this evaluation. But even for n equals 4, it's very, very difficult.
So it currently doesn't seem that it just follows directly from your method?
No, we don't see that.
Okay.
That would be amazing, but at this point, the best we can do is just to derive the Zagier's formula and Murakami's formula.
Okay, I see. Cool. Thank you.
There's this magic step, right, where you take the integral of this arcsine power and arccosine power, and that gives you somehow 2 to 2, 3, 2 to 2, 2.
Yes. Actually, it's like, imagine, okay, so this guy here is like gluing. You see, you have this guy here is like gluing to the side. Because I proved these formulas, both formulas in a special case, and I didn't know how to glue this tail multiple of harmonic numbers. In fact, this is where Lee came into play, and he was like, oh.
Yeah, so there's a power of 3 that comes out when you take the integral.
It's here. Here will be the 3. Here will be the 2's, and the other 2's will be here. You see, these are the 2's. This will be the 3 by doing some tricky stuff with the integrals, and these are the 2's again. So I proved in a special case when this did not exist. So I didn't know how to glue this, tail of multiple harmonic sums to the.
So I guess here the question for 2 to 2, 4, 2 to 2 to get some different functions maybe that give you this different weight instead of 3, some 4 maybe, I don't know.
Yeah, probably some tricky stuff.
But then arcsine and arccosine are very natural because they come up from H2 to 2, right? That involves sine, and I think So I think they must be related still with our, yeah, it's very interesting. But sorry, I just wanted to ask you, I think is there a very good reason why one cares about identity for 2224, for instance? Because at least for 2223, 222, there's this Brown result, right? That every MZV of weight K can be written. Okay, but what about?
In fact, there are some other what they are called higher order multiple zeta values identities in string theory. This is just basically what I'm telling you from a conversation that I had with Don Zagier some time ago, 5 years ago, and he actually told me that he needs this evaluation zeta of 2 just in this special case. He needs this. For m equals 3, well, you'll know it for m equals 4, 5, and so on.
I guess what I'm asking, although it's probably a bad question for me, there's some Brown type result where not the vector space of MVZs of weight K, but maybe some bigger vector space, or I don't know, some different vector space over Q. Maybe that one, all the elements can be written as MVZs with 2, 2, 2, 3, and 4, or I don't know, some result that involves numbers that are above 3, or I don't know if that's the right question. I imagine that would be a reason to care about an identity like this.
Probably. So far, nothing is known regarding that aspect. So what people are interested in right now, they want to see the shuffle regularized identities of Zagier shuffle regularized or Stoffel regularized, when you actually put the divergent values as well into this. So anyway, it's not many things are known at this point. So, as you can see, these identities are pretty hard to obtain.
And about Murakami, sorry, the first step in the proof, so before his formula.
This one.
The step where he proves that the t values, no, even before.
In his proof, yeah.
The t values can be written as a combination of the multiple zeta values. Was that the first step?
Yes.
And then he uses Brown?
Yes, he mimics exactly Brown. So he considers the motivic multiple t values, and then he takes the period map, and then he wants an identity, and then he goes like, okay, we cannot, the motivic setting is limited, so we have to go through this kind of evaluation of like Zagier did.
So the first theorem, this theorem has motivic proof, whatever that means. I don't know anything about that, but it's not some elementary.
You mean the first theorem?
The first thing that you wrote in this slide, yeah, the first.
Yeah. It's not elementary. It's uses motivic arguments.
Okay.
Yeah, so I in fact also have a question, but yeah, I was just checking the slides. So probably, so do you know any generalization of Brown's result? Because his paper title is called mixed theta motifs over Z, right? I mean, probably one actually ask like, can this be generalized to an arbitrary number field? Like to everything.
I don't know. Honestly, I'm not sure if they. I don't think they did anything like that.
And also,
I'm not.
Yeah.
That would be to an arbitrary number field. So
I don't know what kind of multiple zeta value equation is related to this arbitrary. I'm not sure.
Yeah, I don't know.
Okay, another question is like, You said that Zagier conjecture is true for k equals 5.
No, I said if I want that to be true. No. They didn't even prove that.
Okay, so that's not even true.
No,
Okay.
if we want that D5 to be 2, then this will be equivalent with that, which we don't know.
Okay.
So what we know that D5 is less or equal than 2. But if we want to force D5 to be 2. So
okay.
actually, that's actually a good point that you brought up, because Brown's theorem will give you the upper bound, right? So in this way, this will tell you that from Brown's theorem that the dimension of Zk is less or equal than Dk. But you want this, which we don't know.
Yeah, and also this is how how Zagier conjecture his result, right? Because there's T to the power, T to the 3's power. So 2 and 3 appears because you have there 2 and there 3, right?
Yeah, exactly.
I guess this Brown's theorem was already conjectured by Zagier, right?
No, by Hoffman, 97.
Oh, Hoffman. Okay, sorry. Probably Hoffman's earlier. I guess when Zagier made his conjecture, he definitely had some kind of a idea.
You mean the dimension conjecture? Yeah, it was by Zagier, but this Brown theorem was conjectured by Hoffman.
Yeah, I mean, so I'm thinking Zagier probably already also had this kind of a feeling that.
Yes. This was actually.
I'm not sure. Just guess. Okay.
It was a huge conjecture.
Okay, and so Brown's so this time less or equal than dk is really a corollary of Brown's result, right?
Yes. Yes. It follows from yes. Yeah. It follows from as a corollary, but it was proven even before by Terrasoma and others.
Okay.
I think Terrasoma has a paper in Invenciones where he actually proves this upper bound. But it follows from as a corollary from Brown's result.
Again, I have another naive question. You have these shuffle and stuffle product identities. Is there some product formula for multiple zeta functions? There must be, right? Something like Euler's product formula, product over primes.
Yeah. Basically, you want a Euler type formula for multiple.
It's like it's even useful, right, for product formulas for zeta.
But you don't have anything like that.
So there's nothing like that. Yeah,
it's like asking if you can factor a
an Euler product.
If you have a factorization of a polynomial with multiple variables into a product of linear factors, like it's similar to that question.
Yes.
Yeah.
Huh.
So, in fact, there are plenty of conjectures here. For the Riemann zeta function, there is a functional equation, right? So basically, there is a conjecture if multiple zeta values, are there like functional equations in the Riemann sense for multiple zeta values? How many of them?
They're not. When I was probably like 5 or 4 years, I'm not sure. I heard who is that? Gofield. He will talk about this multiple Dirichlet series, and they had this kind of wild group action and Dorian Gofield.
Gofield. Okay. Yeah.
Yeah, I think they had some result on this kind of.
But I want to go. So the thing is that we don't know for multiple zeta values if there exist functional equations. How many of them are there? Like, for example, recently I found out, and to my surprise, I thought for even double zeta functions, there are no such functional equations, but in fact there are. And there is one discovered by this Japanese guy Matsumoto, but it's not it's not the correct one. So it's not like, it doesn't look like the Riemann one. So, and I just found it recently. It's a very, I don't know. In fact, he would generalize it for double L functions, but that's it. For triple zeta functions, no way. Nothing is known.
Let me see. Yeah. Okay. Probably let's first let me ask Ilya, Cosmin, do you have more questions?
No, I'm happy.
Okay, then let's thank Cezar first and end the talk officially.
Thank you.
Thank you, Cezar. Really beautiful talk. Super
Yeah.
nice.